All right, so I'm Vance, and I'm going to talk about the need for predictable speed in real-time automotive systems. And when we're talking about speed here, we're talking about the computers inside of these cars that power all of the sensors and everything that allow them to make decisions about how to drive. So computers have been in cars for a long time, doing lots of different things, like managing the engine, the emissions, the transmission, even your radio, all different computers, but we're not going to talk about those. We're talking about the computers that make something like the Google autonomous car work, except we can't buy the Google car, but we could buy something like the Tesla. So actually, General Motors is paying for a lot of this research, and it should probably be a GM car. In the Tesla today, there's a lot of these things called advanced driver assistance systems, and these are like the Super Cruise or automatic brakes that you might have seen on TV. All of these things take input from sensors on the car and then decide what to do to help the driver out and make driving safer for everyone. So all of these sensors come together to build a model like this that the car can make decisions on. This is from Google's autonomous car. And here the car is trying to make a right turn and go down the road, but there's all these cyclists passing on the right. So the car needs to know, hey, don't turn right until they're gone. Otherwise, you could kill someone, which is bad. To formalize our problem a little bit more, in our case, we're just looking at input from cameras. So we have images coming in at the frame rate of the camera. So let's say 30 frames per second. And we need to decide, okay, what parts of the image can we hit and what parts can we not hit? In these labeled images, we don't want to hit the boxes because those are other cars. But the rest of it is just the highway, so that's fine to drive on. No. You don't want to hit the wall either. And there'll actually be lots of different applications running on the system at the same time. So maybe like a wall detector or a car detector or tracking the little white lines on the road so you know to stay in the lane. And the really important applications like tracking cars in front of you are safety critical, and they need to perform deterministically so that when you execute this program, you know it will finish within a time bound, and you can decide, should I stop or should I keep going? Is there a car getting closer to me, or is everything safe? So this is a real-time system. We need to execute our programs and decide within a time bound whether what we should do next. So if we're looking at our sort of simple scenario here, we have our cameras generating frames periodically, and we want to process each frame before the next frame becomes available to process. So that means the worst case execution time of processing one frame is 33.3 milliseconds. So we can draw this sort of example out on a timeline just to visualize all the things that can go wrong. At time 0, we release the first frame. It becomes available from the camera, and we do some processing on it. When the box ends, it means we're finished processing. And then at time 33.3 milliseconds, the next frame is available. We can process it. If the runtime of our program is variable, it means that the second time we execute it could have a different runtime. So this one finishes a little bit sooner. Then at the next time, the third frame becomes available. And if this frame takes too long, we could still be working on it when the fourth frame becomes available. In our system, we have to process each frame before we can start on the next. We can't just drop the next frame, or we could, but we're not going to. So that means it's going to delay the next frame, and possibly that frame could delay the frames after. So this type of thing can cascade, and if it can cause big delays in the system. In this case on the bottom or up at the top, we say that the system is overutilized because the worst case execution time is greater than the period where we measure utilization on a scale from 0 to 1. And we don't want to design a real-time system that's going to be overutilized. So if it wasn't already kind of clear, cars are real-time systems because the computers we put in them need to be better than a human. So humans have a worst case execution time when they make decisions about driving of about 700 milliseconds. And yeah, we need to bound all of our tasks by at least 700 milliseconds, but for a lot, the ideal deadline will be a lot smaller. So say if we were backlogged and we had a huge queue of images to process before we could make a decision, then we could slam into this car and then 5 minutes later realize, oh, we should have applied the brakes. So in this project, we're using this NVIDIA Jetson TK1. It's unique, sort of, because it's got a GPU and a CPU on the same chip. It's designed for applications like use in cars, and it's pretty cheap, so it could be used in the average consumer car, not something really expensive like a Tesla. And we want to find out, is this platform actually good enough to do the kind of work that we're trying to do? So to do that, we did a lot of different timing experiments to measure the worst case execution time of different programs that would be used in these automotive systems. And we have lots of different sample programs, but just to make it really easy, I'm going to talk about matrix multiplication, which is a fundamental thing you could do on a GPU, and it's probably going to show up in a lot of different computer vision data processing things that go into autonomous driving. So in this experiment, we took different square matrices with 2 to the 10th up to 2 to the 20th elements, and we multiplied them 10,000 times and just timed how long it took. So if we plot our results on a graph with the input size on the x-axis and the runtime on the y-axis, we see that as we increase the input size, the total observed runtime goes up as well, which is kind of makes sense. But these error bars represent the worst case execution time. And in a real-time system, we have to use the worst case execution time as our upper bound for any time we run the program, because we can't predict beforehand how long the program's going to run. And we don't like these really huge error bars, because if our target is 33.3 milliseconds, some inputs might be this big, and we just can't use them on our system because the worst case time is too big. So we want to lower the worst case time to the average time, and we need to look at what's causing the worst case time to be so big. In our system, we think that the unpredictability is just due to the inherent structure of the system. So we have a CPU and a GPU on the same chip. The GPU has a copy engine which moves data from the CPU. Like you have your image, you need to do some algorithm on it. We use the copy engine to copy the image over. And then we have the execution engine that will actually run the GPU program. So the CPU gives the image to the GPU, tells it to compute. And then while the GPU is off doing its work, we don't know how long it's going to take. But when it finally finishes, it tells the GPU, and we have our result available. Another source of unpredictability is that since the CPU and the GPU are on the same chip, they share memory, and we're going to look at some of the unpredictability there. So if we look at just the time the program spends in the execution engine, we see kind of the same shape as before, except now the worst case runtime is not off the screen, it's a lot lower, where before it was that red line that goes way off the screen. So this isn't the overall program, this is just one part of it, but there's something between the top of those error bars and the red line that's taking up a lot more time, so we need to dig a little deeper. If we look at the copy engine, it's that line down at the bottom of the screen. It's actually not very variable at all, and it doesn't take much, we don't spend much time doing copies. So maybe there's something else. Yeah, and it definitely doesn't account for, if you were to add the execution engine and the copy engine, it doesn't account for all of the worst case time we saw. So we should look at our shared memory, since that's all that's left. By default, in the typical programming model, since GPUs are normally discrete units from the CPU, you have your image on the CPU side memory, and then you allocate memory on the GPU, you copy it over, and then you do your execution. Since our system shares memory, we don't have to do any of that. We can just basically send a pointer. We just tell the GPU, hey, look at the CPU memory, and use a pointer to that. So if we time the program again, implemented with 0 copy, and compare it to the original, the runtime isn't that much better, which isn't surprising since the memory operations didn't take that much time. But what's really important is that the error bars are a lot lower now, where before they were way off the screen. And this is the entire program. We're not leaving anything out here. So this is good. So in conclusion, if we are able to effectively manage our shared memory using something like 0 copy or other techniques to alleviate contention in the memory, we can lower the worst case runtime and make our GPU programs more predictable. There's still a lot more work to do with autonomous driving. Like, even if we can make our programs behave deterministically, then the algorithms and the decisions we make based on the models we build have to make the right decisions. Thanks.
Questions? When you're estimating these errors, for example, you had the error bars, were those experimental, like standard deviation, or did you do theoretical work where you kind of found?
Right. So here, in order to get the worst case execution time, we just have to measure. We do a lot of different experiments and measure the time.
Can you detail again on that graph what the improvement was for the 0 copy of copy? And so the error bars on there are the new worst runtimes, and the red lines are representing your old worst runtime?
Right. There's not a good average time improvement, but our real goal is to get the worst case runtime closer to the average, because the average is kind of inherent in the program that you're running.